Chem 106, Chapter 18, Chemical Thermodynamics, Lecture 1. Spontaneous is a term that we use that represents a change that occurs without outside intervention. Spontaneous changes occur only in the direction that leads to equilibrium. So for it to be spontaneous, it must be in a way that leads to equilibrium. We can readily recognize many chemical reactions that are spontaneous by the evidence that we observe of them happening. And a common feature of these reactions is that they are exothermic, but not all spontaneous reactions are exothermic. It's only a common feature. The evolution of heat, exothermic, is not sufficient to say that it is spontaneous. Entropy is a term that we use to describe the randomness, or some people use disorder, which is not a good word, a randomness within a system. And so we can say that in a spontaneous process, energy goes from being more concentrated to being more dispersed. What we do with this idea of entropy is that we take, in chemistry at least, a set of molecules and we spread them out so that they have as much distance and randomness about them as possible. The second law of thermodynamics states that a spontaneous process is one that results in an increase in entropy, disorder of the universe. From its beginning, where it was the most concentrated and organized, until now, some 13.8 billion years later, the universe has expanded and has tried to put most of the universe, most of the objects in the universe, in as random of position as possible. Because thermal energy is caused by the random motion of particles, potential energy is dispersed when it is converted to thermal energy. And so we have an equation that describes that, where the change in the entropy is represented by a capital letter S, and delta, of course, means change. So delta S is our term. Just like where we had delta H for enthalpy, we have delta S for entropy. And so delta S is the change in the entropy of a system. The Q reverse is the heat transferred under reversible conditions. Remember Q from thermodynamics that we talked about in calorimetry. Q is heat energy. And so under reversible circumstances, we use Q reverse. And T, of course, is the Kelvin temperature. And the units on the change in entropy are joules per Kelvin. To understand entropy, we go down to the molecular level. And so energy is transferred as heat between hot and cold atoms that are in contact with each other. And don't take atoms too literally, just say particles, because of course most things are molecular and so on. But so it really should be that energy is transferred as heat between hot and cold particles that are in contact with each other. And we use the term microstate to describe the different ways that quanta of energy are distributed across all of the atoms in the sample. Each particle in a sample, especially in a gaseous sample where there's minimum potential energy and maximum kinetic energy, then all of the molecules are fairly independent of each other. They do collide, so they say they are in contact when they collide. But in general, particles, especially of a gas, are about as random as you can get because most of their energy is kinetic rather than potential. And so whatever any individual particle is doing at any given time, we say that it is in a microstate. And so Ludwig Boltzmann proposed that the entropy of a system, the dispersal of the energy at a given temperature, results from the number of microstates available. As the number of microstates increases, you can imagine if we had a system where there was only one or two atoms or molecules, and so under Newtonian rules, we could kind of figure out where they're going to be and when they're going to collide, through, the future and all. But what happens if we go into chemistry level, where now you're dealing with a mole of particles, 6.022 times 10 to the 23rd, all in their own microstates? As the number of microstates increases, so does the entropy of a system. As you get all of those 6.022 times 10 to the 23 particles doing their own things, you're approaching about as random as you can get. And so the entropy of the system has increased because, remember, entropy is a measure of randomness within the system. And I do say system is the what contains all of the particles. So an equation to help describe this, where S is the entropy of the system, the K is the Boltzmann constant. And this constant has a value of 1.3806503 times 10 to the minus 23rd meters squared kilograms per second squared Kelvin. This is a value you do not need to memorize. All of this material here in the beginning is theoretical information for you so that you have seen this before. This is not on the exam per se. I'm just trying to explain entropy first before we do a couple of problems. And so the description of entropy then within a system is Boltzmann's constant, which is a proportionality constant related to the number of microstates, and of course then the natural log of W, which is the actual number of microstates within the system. And that way we can calculate entropy that way. But that's not really doable because honestly nobody will ever know the actual number of available microstates because as each particle moves, it enters a new microstate. So every time a particle does something, it's in a new microstate, and you've got 6.022 times 10 to the 23rd microstates all changing constantly, so that of course increases unbelievably. So it just is not really practical. That's why, just like with enthalpy, how we did the change, we will only talk about entropy as a change as well. But the sheer entropy within a system is related to Boltzmann constant and the natural log of the number of available microstates. That's a lot of information. Okay, so in many processes, it appears that the dispersal of matter also contributes to spontaneity. When a gas expands to fill a container, the average energy of the sample and the energy for the particles in a given energy range are constant, but there is an increased number of microstates, and those microstates are more closely spaced than before. All right. Summary. According to Boltzmann's equation for entropy, entropy is proportional to the number of ways that energy can be dispersed in a substance. There will be a change in entropy if there is a change in the number of microstates over which the energy can be dispersed. And given that in this universe everything is in motion, there is nothing in this universe that is not in motion, and if it's in motion, it's changing microstates. Therefore, it just becomes unbelievably difficult to even imagine to calculate something like that. And so our focus is on the change in entropy, and we shall be mainly concerned with the dispersion of energy in systems and surroundings during a physical or chemical change. Physical change such as change of state, chemical change in reaction. So we actually rearrange the atoms by bonds. All right. The third law of thermodynamics, as defined by Ludwig Boltzmann, states that a perfect crystal at 0 Kelvin has 0 entropy. That's because it would be the most ordered it could possibly be. Now remember, 0 Kelvin is only theoretical. As you remove heat energy, the temperature goes down, but that's asymptotic. It approaches the x-axis but will never ever ever touch it because there will always be some form of heat energy available. So getting to 0 Kelvin is impossible. But theoretically, if you could, then your substance that would exist at 0 Kelvin would be free of entropy because it would be a perfectly aligned crystal that has no disorder whatsoever in it. So raising the temperature of a substance corresponds with adding energy as heat. Thus, the entropy of a substance increases with an increase in temperature. Conversions from solid to liquid and from liquid to gas typically require large inputs of energy as heat, and so consequently there is a large increase in entropy. Solids have less entropy than liquids. Liquids have less entropy than gases. Gases have the most entropy because, again, there is almost no potential energy. It is almost all kinetic energy in those particles. But the one that has the least, and you really want to probably write this down, because it's not said here explicitly, but there's another form here of aqueous that we've been using all along. Aqueous, believe it or not, has the least amount of entropy because in an aqueous solution, your solute, each particle of solute is solvated by the solvent. Therefore, it takes a whole bunch of solvent molecules to surround and cage each particle of solute. That creates a lot of order within a system. And so aqueous solutions actually have less entropy than solid materials do. So the least entropy is in aqueous, the most entropy is in gases, and then solid and liquid as the condensed phases have medium amounts. Okay. Standard entropy values, notice the little degree symbol on there. That means standard state. So the standard state of a substance is its state under a pressure of 1 bar, which is about 1 atmosphere, 1.01325 atmospheres, and the temperature under consideration. Usually for standard state, that means for us 298 Kelvin, 25 degrees Celsius. So the standard entropy is the entropy gained by converting it from a perfect crystal at 0K to a standard state condition. So in theory, at 0K, it would be perfect and have no entropy. But since everything in this universe is imperfect, because there is heat energy and there is constant motion, then that entropy represents that change from perfect to imperfect. And the units on entropy are going to be joules per Kelvin mole. All right, and so again, you could find lists of these. The textbook, if you have one, any general chemistry textbook will have thermodynamic tables as an appendix in them, or you can find them online. So for the supplemental practice problems, either refer to the textbook, or you can find these tables online, or I might have even put one out in Blackboard for you. I don't remember. But if there is one, then it's for your use. But on the exam and such, then I will provide the information directly. You can't bring anything with you to that. All right, so as we've already said, entropies of gases are larger than those for liquids and of course even for solids. And aqueous has the least of it. I'm sorry. The aqueous has the least. So make sure you make a note somewhere in there, because that's an important idea, that aqueous has the least amount of entropy of these kind of things: solid, liquid, gas, and aqueous. So, all right. For a given substance, a large increase in entropy accompanies changes of state, reflecting the relatively large energy transfer as heat required to carry it out. But notice again, when we say that, that's in either direction. It just now is going to come down to a matter of sign, and we'll discuss that in a minute. But first, there is an equation. This you do have to know. So highlight this and write it out. Make sure you understand it. But you've already seen it when you did thermodynamics before, when we did this with enthalpy back in General Chemistry 1. This is the same idea, that the entropy of reaction is the sum of the entropy of formation of the products minus the sum of the entropies of formation of the reactants. You've already seen this. It's just that it was with enthalpy instead of entropy. And remember, with entropy, these units are in joules per Kelvin mole. All right, so we could do this, and so why don't we go ahead and do this now? Yeah, let's solve a problem. So let's go to lecture problem 1 and solve that. Lecture problem 1 has us calculate the standard change in entropy for the hydrogenation of ethylene to form ethane at 25 degrees Celsius. So the given equation then, C2H4 gas, hydrogenation reaction, it means we're going to use molecular hydrogen. And in organic terminology, this is different than solution terminology. In organic terminology, using molecular hydrogen to hydrogenate something, what that is called, or what we're doing then in process, is what's called saturation. So we get C2H6. We've saturated the molecule with hydrogen now, and of course that's a gas. All right, so you're given a table here, just like you will be on the exam. So you've got this, and you've got a table, and we remember, getting ahead of myself there, that the enthalpy, or entropy, now we're doing entropy, of reaction is the sum of the formation of the products minus the sum of the formation of the reactants. The only thing that's different here is that, remember, for enthalpy, elements in their standard state always had an enthalpy of 0. Well, not here. Because entropy is a measure of disorder and all, and everything has disorder, even elements in their standard states have disorder. Because remember, the idea of the change in entropy came from 0 Kelvin to the standard state, and so disorder was engendered in that transition. So even elements in their standard states have entropy. All right, so let's solve this. I use brackets around here. So the product is C2H6. And remember, we're going to use how many moles there are, too. In this case, there's 1 mole, and I know it's 1 to 1 to 1, but you still need to write this out for where there aren't, where these actually have coefficients that need to be worried about. So 1 mole, C2H6, I look in the chart, and I see the value for that is 229.5 joules per Kelvin mole. All right. And that's the only product. So then minus, and I'm going to give myself some room here. For the reactants, 1 mole. C2H4 is 219.4 joules per Kelvin mole. Plus, because remember, this sigma is a plus, it's the sum of these things. And so now for hydrogen, there's 1 mole. And for hydrogen, that's 130.58. Remember to be doing these along with me so you know what you're doing with them. And then we'll close brackets. This is going to give me then 229.5 joules per K minus the result of this, which is 349.98 joules per K. And that's going to leave me with a result of negative 120.48 joules per K. As always, the last step is to round accordingly. And when I look at this, when we multiplied, that's times something that has no significance because that's infinitely significant. So what we ended up doing then is decimal places. This had a 1 decimal place, and here's a subtraction operation that had 2. So our final answer can only have 1. That 8 makes that 4 or 5. So approximately negative 120. Oops. 120.5 joules per Kelvin. Okay, and so now you notice there's a negative sign on here. What this means then is that positive values indicate an increase in entropy as the reaction goes forward. Negative signs indicate a decrease in entropy. So for this reaction, what I want you to notice is that there was 1 mole of the C2H4 and 1 mole of the H2, both as gases. And we combined them to make only 1 mole of the gas product. So where we had 2 moles, which would have had, way more microstates than simply combining as 1 mole. Therefore, there was a net decrease in the entropy, and that's reflected here in this sign of negative. So a positive sign on the change in entropy is a good thing because that's what the universe wants, and that corresponds to an increase in entropy. A negative sign corresponds to a decrease in entropy. We've made the system more ordered. It was less ordered on this side, and we forced it to go more ordered. And you can see that, this definitely would not be spontaneous. Whenever you put ethylene and hydrogen gas together, you have to put it under high pressure and high heat in order to force this forward. It does not want to spontaneously because, of course, that's not the way the universe works. The universe is all about becoming more disordered, more random. And so this sign is definitely negative. Going back to the outline. An increase in entropy is observed if the product side of the reaction contains more total moles of gas. And remember, that would be a positive sign on the entropy. A decrease in entropy, therefore a negative sign, is observed if the product side of the reaction contains fewer total moles of gas. All right. Entropy changes in spontaneity then. And so here is explicitly, about the standard entropy change for a system. A positive value indicates that the process is favored, and a negative value indicates that the process is disfavored. So those are specific terms that we use for entropy, favored and disfavored. And the universe wants to have an increase in entropy. Therefore, a positive value means the system results in more entropy, more randomness, therefore that is favored. A negative value means that there is less randomness, more order, and therefore that is disfavored. Processes in which both the standard enthalpy and entropy changes favor energy dispersal are always spontaneous, but we're going to talk about that in the next lecture. So right now, what we want to do is, let's see. I just want to be sure here. Let's do the next lecture problem, because I want you to see, by what we've just talked about here and here, tell me about some systems. So we're going to do lecture problem number 2. So let's switch back here, clear this out, and look at lecture problem number 2. It says predict the sign. And notice it's predict. We're not trying to come up with a value. We just want to know whether this is a favored or disfavored entropy situation. And so, oops, get the color back here. All right. N2 gas plus 3H2 gas gives us 2NH3 gas. All right. So whenever you're going to predict the sign, first of all, you got to remember that gases have the most entropy relative in terms of states. Aqueous has the least, then solid, then liquid, and gas has the most. All right. So what you want to do in answering a question like this is count the total number of moles of gas on each side. Focus on the gas because that's the most entropy. And so there's a 1 out front here, so there are 4 moles here and only 2 moles here. There's a net decrease in the number of moles, and therefore that is disfavored because it is a gas that has high entropy over here, low entropy over here. Disfavored, so the sign should be negative. Hopefully that makes sense. The next one, calcium carbonate, which is a solid, decomposes to form calcium oxide and carbon dioxide gas. Okay, so once again, when we're trying to figure out whether an equation is either favored or disfavored, and the accompanying sign, then what you want to do is you want to come up with, determine the number of moles of gas from each side. This left side has only a solid, therefore there are 0 moles of gas. But the product side, carbon dioxide is a gas, and there's a 1 in front of it, so there is 1 mole. Therefore, from left to right, the number of moles of gas are increasing, so this is favored, and the sign will be positive. All right, let's look at acetylene. 3 moles of acetylene gas are going to come together magically somehow to form 1 mole of benzene. Yeah, not going to happen. And so again, from an entropy situation, let's have a look at this, right? Here, that's a gas, and there's 3 moles of it. Over here, there's a 1 out front, so there's only 1 mole. 3 moles to 1 mole. For way more reasons than just entropy, this is not going to happen. But just because all we're talking about is entropy, then 3 moles to 1 is disfavored, and therefore has a sign of negative. Last one. Al2O3 solid plus 3H2 yields 2Al solid plus 3 H2O gas. And we're saying gas because this is a very thermically charged reaction. So when the water forms, it's definitely in the form of gas. All right, so again, look at each side separately. And over here, we see there are 3 moles of gas. And over here, we see that, there are 3 moles of gas. Oh, no. So, is it favored or disfavored? There's 3 moles of gas here and 3 moles of gas here. Now, technically, I would not do this to you on an exam where, the correct answer would be, something like this, except for to say, because what we would say is just by looking at the number of moles of gas, it's neither favored nor disfavored because it's the same. But if you go into the nuance of it, like I said, I'm just bringing this up. I won't do it to you. I added this problem on purpose to show you that sometimes there is no change. So there is no favor, disfavor from the point of view of increasing or decreasing the number of moles of gas. But if you look at this, this is hydrogen. So all the molecules are H2. So HH, if you look at the Lewis structure for it. Over here, H2O. All right, that's more complicated than this. And so, in essence, this is going to have more microstates, this water, than will these hydrogen molecules. They're very simple, and so they don't have much in the way of changing microstates. But here, I've got all kinds of internal things and external ways that the water molecule is going to act and react. And so what'll happen then, and like I said, I'm just bringing this up, you won't have to do this. This technically, because this water has the capability of entering into more microstates than does this H2. Because, again, I can bounce this hydrogen, I can bounce this hydrogen. Here I can only bounce once, but here I can bounce twice in these bonds. I'm just talking about sheer vibration of bonds. This has more to bounce. So that's more complicated, and that means more microstates. So really, you would assign a small positive value to this one because of this. But that's more advanced. I'm just pointing out that it's not that simple. But for you guys in this freshman version of it, it's going to be fairly straightforward. I just want you to see that there is the potential where the moles don't change, and you have to go into more nuanced ideas to find out what it's going to do. This concludes Lecture 1.